All right, so we're talking about order matters. So if I say for all x, there exists a y, and let's talk about a statement that depends both on x and y. And let's say that p of xy is equal to has to start with a p. X pretends to be y. Okay? I just made up that function. I hope it's not too retarded when we do this example. Okay, so in this case, this statement said, this is the way I read these. For all, I read as a for each. For each x. And there exists a y, I read is there. I read it as I can find a y. So if I read this statement, I read it to say, for each x, I can find a y value that makes p of xy true. That's how I read this statement right here. For each x, I can find a y value that makes p of xy true. Now in this case, if p of xy is x pretends to be y, and let's say that x and y are people, okay, they don't have to come from the same domain, but I'm telling you that they do in this case, then that means for each person, then there is another person. So for each person x, I can find another person y so that x has pretended to be y. Okay? And actually, let's just make this a little bit simpler and change it from pretend. Let's just put likes. Okay? Even though p of xy doesn't start with an L for likes.
Is that like saying every person has one and only one best friend?
No, it's not. It's saying at least. It's kind of
At
like
least one best friend.
So in this case, if I read it again with the likes, for each x, I can find a y so that x likes y. So that means every person, there's someone out there in the world that they like. Okay? Does that have to be, does everybody have to like the same person?
No.
No, everyone can choose someone different to like, right? I can like my brother, you guys don't have to like him. Or vice versa, right? So in this case, each x has a y value, and that's why I read it like this. For each x, and the x is the most important thing because it comes first. It's the independent variable because it came first. So it gets assigned before y does. So if you think about in a program, when you're doing assignments or you're doing a loop, like the for all is just like a loop for every single possible value of x. And this assignment comes on the inside, so that means it can depend on the x value. Right? So y depends on x because it comes second. Now let's reverse the order of this and then see what it means. So if I say there exists a y for all x, p of xy, then this says there is a person, I can find a person y, so that for every person x, x likes y. How many y's are there?
At least one.
There's only one person that's getting liked, right? We'll just talk about one. There could be more than one that everybody likes, but let's just talk about one. There's at least one person that everyone likes, no matter who x is, that same y is going to work for the statement. So in this case, x depends on y because it comes second. So y is independent because it comes first. So in this case, there's about one y value that makes this statement true. There might be more than one, but we'll just say there's at least one. So I'm just going to compare numbers of things. If I have for all x there exists a y, how many y's are there that help make this statement true?
Whole population.
There could be lots, right? So there's possibly as many y's as there are x's. So these statements are very different. It depends on where you put the there exists and where you put the for all. Okay, so we've figured out that where the not goes matters and what order the quantifiers in matters, and it also matters which letter you put where, right?
Tiffany, how do you read that statement at the top?
This statement right here?
The one above it.
This?
Above it. That one.
Yeah, that's the same statement as down here.
Oh, sorry.
But I can find a person Y so that for every other person X likes Y. So I have to read this. I always have to read this as X likes Y. I read this as I can find, and this is a for each.
So basically, there's a person who everyone likes.
Right. So there is a person who everyone likes. That's a perfect English sentence for that. So that's a lot different than saying everyone can find someone that they like. Right? There's a person who everyone likes that's one person.
How could you prove that, though?
How can I prove that they're different?
Well, no, how could you prove that there's one person that everyone likes? I mean, that's like, isn't that going to like infinity? You could not.
Well, I could restrict my domain to a room full of people, and then I could ask everybody who they like and find out if there was one person that everybody liked. Right?
Okay, so it depends on the set.
It depends on the universe that you're talking about. So since we were just talking about whether these two things were the same, I didn't quantify the universe. But if you really wanted to find out, you would need to know. Okay, but a lot of times we don't need to know whether the statement's true or false. We just want to figure out if combinations of these propositions together are going to be true, or when some combinations imply some others. So some of the rules that you've been using can still be used here. So for example, if I have, if I know for all x p of x, and I know for all x p of x implies q of x, I can use implications and ands and ors with my predicates. Okay, if I know those two, you all know a rule that will tell you something else true. Modus ponens, right? So if all the p's are true and all the p's imply q's, then I know that all the q's must be true. Right? So this logically implies for all x, q of x. With for alls, you can do logic and just ignore the for alls. As long as everything is true for everything, then I can just not even think about the for all x anymore. It's there exists that give us trouble, right? If I have there exists x, p of x, and for all x, p of x implies q of x, I can still use modus ponens, but I have to be careful. Right? What happens when I use it? Remember that an and preserves falses, right? So a lot of the time, this thing is going to be false. It's only going to be true for one guy, right? And this is true all the time. So my resulting statement should have as many falses as this does. So it should have a there exists. So if P is true for one guy and P implies Q is true for everybody, then Q must be true for that very same guy. So sometimes I even label this X as 1 to remind myself that it has to be the same as the person that got quantified in this statement. The person that has Q true must have had P true.
Does that rule have a special name or anything?
This is modus ponens. It's the same thing,
Same thing, okay.
but there's no special rule for it, but I'm just saying that whenever I combine a there exists and a for all, I better get a there exists because I'm anding. If I did an or, it would be a for all, right? Because ors preserve the truths.
Can you repeat that again?
Ors preserve truths. So if I have like 1 or anything else, I'm going to get a 1.
Okay.
Right? So if I did there exists X, P of x, or
All X.
for all x, Q of x, then I probably wouldn't really combine these. I'd leave them separate because it wouldn't tell me any new information to combine them.
Okay.
But if I were to combine them, I would say for all x, either P of x is true or Q of x is true. This would logically imply that just by the definition of or, and by knowing that or is going to combine and make sure that all of these are true. So this or statement is always true.
And what was the reason for the above ones?
This is if that was given. I mean these two?
No,
This?
yeah.
Modus ponens is the reason.
Okay.
And the fact that there exists there is by the definition of how there exists works and how and works. So I don't give a reason for that. I just know that if I use it, it can only be true for the things. This statement can only be true where P has to be true and P implies X has to be true.
Right.
And this only happens where it happens to be X1, so this has to be for X1.
Okay.
Because this is automatically going to be true for X1 because it's true for everything.
Okay.
Does that make sense?
Well, that's what implies means, right?
No, that's
P
what
implies
for all
Q.
means. For all means no matter what X I plug in, this statement will be true. P implies Q will be true.
Okay. I got you.
So we're doing a lot of complicated combinations of things that you've done so far. So you have to keep them straight.